Objectives. First, define, identify, and understand types of transformation, translation, reflection, rotation, and dilation. Second, apply geometric transformation to solve real life problems or design projects. Third, communicate ideas about geometric patterns and transformation effectively.
Conceptual framework. Geometric pattern. The art of transformation. Title. Theme. Objectives, which will be discussed by Janiela Maypin. Conceptual framework, or the flow of the topic, which will be discussed by Nicole Pakituan. And the introduction, or the transformation, which will be discussed by our leader, John Bird Marilao. On the other hand, translation, Kim Marie Utek will be the one who will explain this. And reflection, which will be discussed by Althea Novella and Krishna Lover. It would be rotation, which will be discussed by Janiela Maypin and Sabado Miki. And dilation, which will be discussed by Nicole Pagidungan and also, again, John Bird Marilao. And the conclusion will be discussed by Althea Novella.
Geometric patterns are a captivating blend of mathematics and art. They are formed by repeating shapes and motifs, arranged in a systematic and organized manner. These patterns can be found everywhere around us, from the intricate designs on ancient pottery to the mesmerizing structures of snowflakes. It refers to the various ways in which a shape can be manipulated to create a new pattern. The four primary types of transformations are translation, reflection, rotation, and dilation. Transformation, it is a bijection of a set that has a geometric structure by itself or another set. If a shape is transformed, its appearance has changed. There are basically four types of transformation. And as I've said, it is translation, reflection, rotation, and dilation.
Translation is a geometric transformation that moves every point of a figure by the same distance and in the same direction. Like in a real-life example, sliding a chess piece. When you move a chess piece across the board, you are essentially translating it. You are sliding it horizontally or diagonally without rotating or flipping it. Equations example, let's say you have a point x and y on the original figure. To find the coordinates of the corresponding point x and y on the translated figure, x equals x plus h, y equals y plus k, where h and k represents the horizontal and vertical shift respectively. Example, if the original point is 2 and 3 and the translation is 3 units to the right, h equals 3 and 2 units up, k equals 2, then x equals 2 plus 3 equals 5, y equals 3 plus 2 equals 5. The new point after translation is 5 and 5. In summary, translation is a geometric transformation that involves sliding a figure across a plane without changing its size, shape, or orientation. It's a fundamental concept with applications in various fields, including computer, graphics, robotics, and game development.
Reflection is a geometric transformation that flips a figure across a line called the line of reflection. For real-life example, the most common example is a mirror. When you stand in front of a mirror, your reflection is a flipped image of yourself across the plane of the mirror. Equations example. Number 1, reflection across the x-axis. If the original point is x and y, the reflected point is x reflected and y reflected is number 1, x reflected equals x. Number 2, y reflected equals negative y. Number 2, reflection across the y-axis. If the original point is x and y, the reflected point is x reflected and y reflected is number 1, x reflected equals negative x and y reflected equals y. For the summary, reflection is a geometric transformation that creates a mirror image of a figure. It involves flipping the figure across a line of reflection, resulting in a congruent image with the same size and shape but opposite orientation.
Is a geometric transformation that turns a figure around a fixed point, called the center of rotation.
Here is our real life example. We have Ferris wheel. As a Ferris wheel rotates, each car moves in a circular path around the central axis. This is a real world example of rotation.
Equations example. The equation for rotation are more complex and often involve trigonometry, sine and cosine function. They depend on first, angle of rotation, the angle by which figure is rotated. Second is the center of rotation. The coordinates of the center of rotation, usually the region of 0, 0 for simplicity. Simplified example. Rotation 90 degrees counterclockwise around the origin. If the original point is xy, the rotated point is x rotated, y rotated is x rotated is equal to negative y, and y rotated is equal to x.
Rotation is a geometric transformation that involves turning a figure around a fixed point. It's characterized by the angle of rotation in it, and it preserves the size and shape of the figure.
Dilation is a geometric transformation that changes the size of the figure while preserving its shape. Real-life example, photocopy. When you enlarge or reduce the document on a photocopier, you are performing a dilation. So the original document is the pre-image, and the enlarged or reduced copy is the image.
These are the equations examples. Let's say you have a point x and y on the original figure. To find the coordinates of the corresponding point x dilated and y dilated on the dilated figure. First, x dilated is equals to k times x. Second is y dilated equals to k times y, where k is the scale factor. Example, if the original point is 2 and 3 and the scale factor k is 2, then x dilated is equals to 2 times 2 equals 4. Then y dilated is equals to 2 times 3 equals 6. The new point after dilation is 4 and 6. To sum up, dilation is a geometric transformation that changes the size of a figure while maintaining its shape. It involves enlarging or reducing the figure by a scale factor around a center of dilation.
In conclusion, geometric transformations such as translations, rotations, reflections, and dilations provide a powerful framework for understanding how shapes can be manipulated and how patterns emerge. By applying these transformations systematically, we can generate intricate and fascinating designs with underlying mathematical principles. These concepts have profound implications in various fields from art and architecture to computer graphics and scientific visualization, demonstrating the interconnectedness between mathematics and the visual world.